Earlier in the classes we have already learned about electric current, and also in the introduction I told you that electric current is a very useful source of energy. Now, apart from all the uses that we have already learned, there is another use that another reason for it being used very widely. Now we know by the law of conservation of energy that energy can neither be created nor it can be destroyed, but it can be converted from one form to another. And electricity is being used it is preferred because it is very easy for us to convert electric energy into different forms of energy. Like electric current, our electric current can be converted into kinetic energy by using our generators. It can be converted into magnetic energy in electromagnets. It can be converted into heat energy in our various heating appliances, and also it can be converted into chemical energy in electrolysis. So now there's a question that arises in our mind. I have an electrical device, and in this electrical device a constant amount of current or electrical energy is being supplied. Now the question what arises in my mind is, what happens to this current? Now a part of this current is being used to do useful work, and a part of it is being converted into heat energy. Just like, for example, I have a rotating fan. I have a constant supply of current in this fan. A part of energy is used to rotate the blades of the fan, whereas a part of energy is used to it is being converted into heat energy. That's why if you notice, like if a fan has been used for a very long time, if we touch the blades or the rotator, we feel that it has become hot. Why? Because a part of the energy has been converted into heat energy. But in certain devices, like your electric heaters, your electric iron, these devices, they are purely resistive in nature. What I mean is that the entire amount of current that is being supplied to the devices, the entire current is being converted into heat energy, and this is being done because of the resistance of these substances. Now, this conversion of electrical energy into heat energy in purely resistive materials or purely resistive appliances, this phenomena is known as the heating effect of current. So what happens in when electric current flows through a conductor, why is it that it produces heat? In the earlier class I talked about a conductor. How does a conductor conducts electric current? We know that a conductor, it consists of free electrons, and it is because of these free electrons that it can conduct electric current. So when I connect a conductor to a potential difference, because of this potential difference, electrons will move from one point to another. But this movement is not very free, it is not very smooth, because these electrons will collide with the atoms and molecules of the conductor. And when this collision occurs, there is a transfer of energy from the moving electrons to the atoms and molecules of the conductor. And when this happens, the atoms and molecules of the conductor will vibrate rigorously in about a mean position. Due to this, the average kinetic energy of the conductor increases, and which leads to the formation of heat energy. So this is how electrical energy is being converted into heat energy. Now this heat energy that is being produced in a conductor in a resistor, it depends on certain factors. What are these factors? I have the strength of a current. The heat energy that is being produced, it depends directly upon the strength of the current. It depends on the nature of a conductor. It depends on the resistance of the conductor basically. The more the resistance, the more will be the heating effect. And also it depends on the time of flow of current. More is the time of flow, more will be the heating effect. Now, usually in certain devices we don't want this heating effect of current. It is undesirable. But in certain appliances we use this heating effect of current. The practical application of this phenomena, it is used in these devices like your electric heater, your electric iron, electric kettle, and so on. Now, what happens in these devices? In these devices, I have a thin wire of alloy. a thin wire made up of alloy. This alloy, it can be a nichrome wire or manganese wire. What is nichrome? A nichrome is an alloy made by these materials. I have 60% of nickel, 25% of iron and 15% of chromium. So I combine these materials in this proportion. The wire that I get is a nichrome wire, or I can use a manganese wire. What is a manganese wire? Again, it is an alloy made by combining 84% of copper, 12% of manganese and 4% of nickel. Now a question arises, why are we using these wires? Why are we using these materials? Why don't we use other materials? It is because other materials, they do not offer certain, or they don't have certain characteristics as these materials. Let us look at these characteristics or the properties that make these materials an ideal material for heating effect of current. The first property is it provides a high electrical resistance. The resistance offered by these wires is very high, and due to this, as we have discussed, that heating effect increases, or heat energy increases with increase in resistance. So basically, more the resistance, more will be the heating effect. So because these materials have high resistance, they are used in these devices. Another reason is that it does not get oxidized at high temperature. Usually metals at high temperature, they get oxidized, they get burned, but in this case for these materials it is not so. They doesn't get oxidized at high temperature. They have high melting point. They can be heated up to 1500 degrees Celsius. Another reason, like usually when we take metal, when we heat it, the size of the metal increases, they tend to expand. But for this material it is not so. They do not increase appreciably. Even though they are increasing, the increase is very small, it is negligible, and this increase will not affect the device as a whole. Now apart from this these practical application, there is another application of heating effect of current. That is, this effect can be used to generate light energy. That is, heating effect of current can be used to generate light energy. Now we know that if we heat a metal, this metal, when it gets heated up to a certain amount of temperature, it emits light. If it is heated up to 15 degrees Celsius, it will start emitting light. And if it is the temperature is raised up to 22 degrees Celsius, this light will be white light, the visible light. So basically, there are certain materials like a metal, tungsten, which is the metal with the highest melting point. It can be heated up to very high temperatures. So even though if I heat this metal up to 22 degrees Celsius, it does not melt, or it does not get burnt. So a tungsten is a metal which is used in electric bulbs, the traditional bulbs that we used earlier. So what happens, I have a tungsten wire, a thin filament of tungsten wire, which is connected in V-shaped support and which is inserted in a glass bulb. This glass bulb is evacuated back, we have taken out the air, everything from this bulb, and when I pass electric current through this bulb, the tungsten gets heated up to 22 degrees Celsius, due to which it emits light. Now what are the properties of tungsten that enables us to do so? Again, tungsten has a very high resistance. They can be heated very fast. The heat energy, like the temperature rises very fast in tungsten. Another property is that it has a high melting point and it does not get oxidized. So for these three reasons, tungsten is being used as the heating element to produce light. So these properties are important from the exam point of view. They may ask you a question regarding these properties. Earlier, we have talked about electric potential. What was electric potential? It is the amount of work done in bringing a unit positive charge or moving a unit positive charge from one point to other. So mathematically, it was expressed as this. I have V is equal to W by Q. So it is the amount of work done in moving a unit charge from one point to another. So from here, I have my W is equal to VQ. Now this is my electric work. So basically, what is electric work, or when is electric work said to be done? Electric work is said to be done when charges flow through a conductor maintained at a potential difference. So again I am repeating, when is electric work said to be done? It is said to be done when charges are flowing through a conductor maintained at an electrical, at some potential difference. Okay, so from here, we know earlier, like when we did the topic of electric current, we learned the mathematical formula for electric current. I have I is equal to Q by T. So from here I have Q is equal to IT. So I can substitute this value of Q in here. So when I do that, I have W is equal to V. Then instead of Q I have IT. Again, by Ohm's law, I have V is equal to IR. So when I replace the value of V in here, I have W, this is equal to IR into IT. So I can write this as I square RT. Again, if I replace the value of I now in here, if I replace the value of I, from here I have V, I am replacing the value of I. So from here I have V is equal to, this will imply my I is equal to Q by T. So I have Q squared by T R. So these are the formulas that we need to know for numericals. So just keep these formulas in mind. Now coming to electric power. Okay, before that, what is the unit of electric energy? The SI unit of electric energy is joules. The SI unit of every energy is joule. Again, electric energy is an energy. So the SI unit of electric energy will be joules. The SI unit is joules, denoted by capital J. Now, when is 1 joule of work said to be done? Or when is 1 joule of work, electric work said to be done? It is said to be done when 1 coulomb of charge flows through a body, when 1 coulomb of charge flows through a conductor maintained at a potential difference of 1 volt. I am repeating what I am doing here. I am simply replacing the value of V by 1 volt and the value of Q by 1 coulomb. So when I do so, if this is my equation 1, my equation 1 will change in this way. I have my electric work is equal to 1 volt into 1 coulomb, which is equal to 1 joule. So when is 1 joule amount of work said to be done? If my 1 coulomb of charge flows through a conductor maintained at a potential difference of 1 volt. So coming to electric power now. What is electric power? Electric power, it is basically the rate of doing electrical work. It is the rate of doing electrical work. Or in other words, I can say how much work it is, how much electrical work is being done in 1 second. So basically, it is the amount of electrical work done in 1 second. Mathematically, I can represent electric power as this. P is equal to, it is the amount of work done, electrical work done. So W by T. So this is the mathematical representation of electric power. Again, I have different values of W from here. Correspondingly, I'll get different. I have different formulas for W from here. So correspondingly, I'll get different formulas for power. And it is important to know that the SI unit of power is what? So the SI unit of power is what? Now what is 1 watt? Definition of 1 watt. Okay, before doing this, just let me replace let me replace the value of W by the first formula in here. So I have P is equal to, instead of W I am putting VIT by T. So T and T gets cancelled. Basically I have P is equal to VI. So this is one of the formula. So from here I can formulate the definition of 1 watt. What is 1 watt? It is the power generated by a conductor or generated in a conductor when 1 ampere of current flows through a conductor maintained at a potential difference of 1 volt. What I am doing, I am simply replacing these values by 1 volt and 1 ampere, and when I do so I get 1 watt of power. We have already learned that the SI unit of electrical energy is joules, but in commercially these units are not used. So the commercial unit of electrical energy is watt hour. It is watt hour. So I have to keep this in mind, that the commercial unit of electrical energy is 1 watt hour. Now what is 1 watt hour? I have 1 watt hour. This will be equal to 1 joules per second into hour. This will be 3600 seconds. So basically this is equal to 3600 joules. So basically my 1 watt hour is equal to this much amount of energy in terms of joules. Bigger commercial units of electrical energy are my kilowatt hour. I have kilowatt hour and broad trade-off system. So okay, the next topic that we'll do is the power voltage rating. This is an important topic. Why important? Because we have the applications of this in our day-to-day lives. Now, when we purchase any electrical device, maybe a bulb or a charger, we always have a power voltage rating which is mentioned for it. Like usually, like when we purchase an electric bulb, the power voltage rating is this. I have 60 watt and 220 volts. It is written on top of the bulb. Now what is this power voltage rating? It specifies the amount of voltage required for the proper functioning of the device, and also the amount of power, or the amount of power it will consume during its operation. So when I have this 60 watt to 220 volt, it simply means that this bulb will work properly, or it will work at its best if I supply a voltage of 220 volts. If I apply a potential difference of 220 volts, and also it means that in doing so it will consume 60 watt. So basically, what is my power voltage rating? My voltage rating, it specifies the amount of voltage or the amount of potential difference that I need to apply to across the terminals of the device. If I apply such a voltage, it will work to its best. And what is the power rating? It specifies the amount of power it will consume during its when it is working. So this is my power voltage rating. Now I have another topic, which is my electric fuse. Now this is again an important topic. What is an electric fuse? Basically, it is a safety device. Okay, before this, just let us look a certain application of heat energy. I have my heat energy. I can write this as I square R. Let's take an example. Suppose I have a device whose resistance is R. I have a fixed resistance. I have a device with fixed resistance R, and I can vary my current. When I apply 1 ampere of current, the heat energy produced will be R. But if I increase the current to 10 amperes, what happens? The heat energy now produced will be 10 square times of R. So this will be 100 R. So you notice one thing is here. When I increase the current 10 times, the heat energy is increased 100 times. So And we also know that in our domestic circuits, copper wire is used to supply for the transmission of electric current, and these copper wires are properly insulated. Now, although these wires offer resistance, but the resistance is very small, and due to which the heat energy which is being generated by this wire is small and it does not damage the insulation. But however, if I increase the current, or if there is a sudden increase in current, the wire, it gets heated up to a certain extent that it can damage the insulation. And when this happens, two wires they come in contact, and when two wires come in contact, it may lead to short circuiting, which may again lead to fire. Now there are two important terms in here that we need to know. I have the term overloading and short circuiting. I have overloading and short circuiting, or a short circuit. Now what is overloading? Suppose I have a device which works well, or the maximum amount of energy it requires, or the maximum amount of current it requires is suppose 10 ampere. Now for a certain reason, suppose the amount of current increases, suppose up to 20 amperes. So when this happens, this device which works at 10 amperes will get damaged. So what is happening? The amount of current is being increased up to a certain extent that this cannot take in. So basically this device will get damaged. So this situation is known as overloading. That means a sudden increase in current. And what is short circuiting? When the live wire and the neutral wire comes in contact, it leads to short circuiting. So keep these two terms in mind. Now how does an electric fuse work? As I told you, what is an electric fuse? It is a safety device. Basically, it is the weakest point in an electric circuit. It is made up of a wire which can easily melt, or which melts at high temperature. Basically, this wire, it is an alloy made by using 50% of tin and 50% of some other material. So it is an alloy which is made up of this composition, and this particular alloy or this particular wire will it will melt at high temperatures. So basically what is happening, suppose I have a device in here, I have an electronic device in here which works suppose at a heat of 30 degrees, and I have a flow of current. In here I have a fuse. So basically, if the amount of energy, or if the current increases, leading to the increase in the amount of energy or the amount of heat produced, before reaching the device, my fuse will break, therefore leading to the breaking of connection of electric current in here. So basically, before reaching my device, the fuse breaks, which saves my device. Instead of damaging the device, my fuse breaks, and I can easily replace the fuse. So this is the function of an electric fuse. It is used in almost all domestic circuit at the beginning of the circuit. Now another topic is why do we prefer, like in almost every, in most of the electronic devices, resistors are connected in parallel and they are not connected in series. There are two important reasons for this. The first reason is that I can operate different resistors by using different switches. Suppose I have two resistors. Which are connected in parallel. So I have two resistors which are connected in parallel. So in here I can have two different switches. I can have a switch in here and I can have a switch in here to operate these two resistors. So basically, if I want my resistor A to be working and B not to be working, what I do, I put this switch on. And this will remain in the switch off state. So basically my resistor A will be working and resistor B will not be working. But in case of series resistors, in case of series combination, this will not happen. Why? Because in series, in series combination, I cannot have two different switches. If I have a switch in here, if I put this switch in switch off state, both the resistors will not work. There will be no flow of current for both the resistors. And if I put this in switch on state, there will be a current, or both the resistors will work. So basically, I cannot make one work and the other not work. So this is one reason that we prefer this parallel combination of resistors. Another reason is that suppose one of the resistors in here, or one of the devices in here, it gets destroyed, it gets damaged. What happens, even though this is destroyed or this is damaged, this we can still operate with this resistance. But in this case, this will not be true. If this resistance is damaged, I cannot work with this resistance, as my electric current cannot flow through this. So with this, I have completed the theory of this chapter. In the next class, in the next talk, we'll be dealing with numerical problems.